Hello everybody. We now move on to the second lecture on logical deduction in artificial intelligence. In the first lecture, we discussed how we progress from propositional logic or Boolean logic to first order logic or predicate logic. And now we shall see in a little more details what are the basics and what are the tenets and what are the ways in which we work out predicate logic. We looked at these four examples yesterday, and in the previous class we looked at this example of wherever Mary goes, so does the lamb. Mary goes to school, so the lamb goes to school. We discussed about no contractors are dependable and some engineers are contractors, therefore some engineers are not dependable. Similarly, we discussed two other problems and we worked them out. Based on that, we said that as we move on from propositional logic, we introduce the concept of variables, we introduce the concept of predicate symbols. For example, we did goes xy, which represented x goes to y. We also looked at variables where this x and y here are variables. We also looked at constant symbols. For example, in this case, Mary is a constant symbol, lamb is a constant symbol, school is a constant symbol. And we will see that there are other symbols which are like function symbols. And we shall see that later in this lecture. In addition, we identified from the examples that we had that we needed to talk about all and some. So we introduced two new quantifiers or connectors. These are called quantifiers. The first is called the there exists quantifier. The second was called the for all quantifier. And based on that, we solved all these four examples on this side of the screen. And for example, in this one, we said for all x, in this case, for all x, goes Mary x implies goes lamb x, where x is a variable. This for all is the connector, and x is bound by this connector for all x. In this case, x is said to be bound or quantified by this for all. The other two were, the second was goes Mary to school, and the goal was goes lamb to school, and we wanted to prove that this F1 and F2 implies G is always true in order to achieve our deduction. And we looked at all the four examples which we have done. Now let us go on to some of the more nitty-gritties of expressing sentences in first order logic. And how do we use the quantifiers? So I have listed about 6 examples, and let us see how we work out on all the 6 examples. So let us assume that we have a predicate called likes. To indicate that x likes y. So if this is our predicate, x likes y, and this is the only predicate we have here for these 6 examples. So the first one is someone likes everyone. That means we will write there exists x such that for all y likes x, y. Which means that there exists someone x such that for every y, x likes y. This is how we encode someone likes everyone. How do we encode? So we have done this one. Now, how do we encode this one? Everyone likes someone. So what we write is, for all x, there exists y such that likes x, y. What does this mean? This means that for every x, there is some y such that x likes y. The most important thing here to note is that y depends on x. This does not say that there is somebody who, does not say that there is some specific y whom every x likes. It does not say that. It says that there is everyone likes someone, which means that for every x there is some y, and that y may depend on the x such that x likes y. Here is the other one which we were talking about. There is someone specific. There is someone specific whom everybody likes. So for doing that, we have to write that there exists some y such that for all x likes x, y. Note the difference between this one and this one. This one says there is some y, and that y, this y is independent of x. So there is some y such that for every x, x likes y. So this is the difference between, so this one comes here, this one comes here, and this one is this. Everyone likes everyone is a very straightforward one. We write for all x, for all y, likes x, y. We could also write this as for all y, for all x, likes x, y. These two are same. Now, the next one. If everyone likes everyone, then someone likes everyone. Someone likes everyone is this one. No, this one is, there is someone whom everyone likes. Someone likes everyone is this one. So let us say this is F1. And everyone likes everyone is F2. Then all we are saying in this one is F2 implies F1. I want to put a note here. When we write this part, what we are trying to say is we will write it this way. So the first one says someone likes everyone. So there exists x for all y likes x, y implies for all x, for all y likes x, y. Now please note the following. Please note that this x is related to this x and this x is related to this x. This y is related to this y is related to this y. Therefore, this y and this y are actually different. It is like the scoping rules in a programming language. So if we replace this by y1 and this by x1, it means the same thing. So the quantifiers also have what are called its scope rules. And these scope rules indicate which variables quantify or bind which other variables. Then there is the last one in this query. If there is someone whom everyone likes, then that person likes himself or herself. I leave this as an exercise for you to do. Now, let us come to this very interesting point, which I call the laws of negation. The law of negation, which some example which we had seen earlier in the previous day was, not for all x, px is identical to there exists x not of px. This says for all x, px is true, and this says for all x, px is not true. If for all x, px is not true, then there must be some x for which px is false. So these two are equivalent. How they are happening? Actually, the for all quantifier is the same as an AND operator for all elements which are existing. That means for all x is the same as AND I for all x. So for all x, px is the same as this being replaced by AND of px for every x. Similarly, the there exists operator is again the there exists operator x is the same as OR of I for everything. So this is an OR operator, the there exists is an OR operator, for all is actually an AND operator, and therefore for them the De Morgan's laws hold. By the way, there is historical evidence that De Morgan's laws were also found out in India, probably a little earlier than De Morgan himself. That is for you to look out in the history books of history of mathematics. So we see that quantifiers for all there exist variables and predicates enable us with a lot of power to express very interesting language sentences in languages. Sorry, just before I complete this, I went back and saw that there was a small typo in this one. So when I said that F2 implies F1 is if everyone likes everyone, then someone likes someone. So everyone likes everyone is F2 here, and someone likes someone is F1, and I had said this is fine, and then I had written this side implies this side implies this side, which actually it should be this side implies this side. This is the small mistake because it is F2 implies F1. So this is what it says: if everyone likes everyone, then someone likes everyone. So the implication should be from F2 to. We now come to some more things. For example, if gxy indicates x is greater than y, then if we are to quote this sentence which says if x is greater than y and y is greater than z, then x is greater than z, which says that for all x, for all y, for all z, it says if greater xy and greater yz implies greater xz. And this quantifies over all variables x, y, and z. But if we are to express a sentence like this, the age of a person is greater than the age of his child, then we have to express age. For this, we introduce something new. We introduce a function symbol. Till earlier, we had introduced constant symbols, like we did Mary, Lamb, Aisha, etc. Now, like a proposition moves to predicate logic, similarly, a constant symbol A can be generalized to use variables to have a function bx, where x is a function. So similarly, we can have x as a function. For example, in this case, we define a function called age x, where x is a variable. So here this is a variable. This being a variable, age is a function symbol. Being a function symbol, it is just like a proposition or a Boolean variable gets generalized to a predicate with arguments. A constant symbol gets generalized to a function symbol with arguments. Now, having a constant symbol like this, now we can write that we can now write the second case as follows. For all x, for all y. So for all x, for all y. And if we have another predicate other than this one called child, xy, to indicate x is a child of y, then here we write this as for all x, for all y, child xy implies, what does it imply? It implies that the age of that person, so greater than age of y, comma age of x. So this is how we define this example. In order to do this example, we introduced one function symbol called age and one new predicate symbol called child xy. And we said that for all x, for all y, if x is the child of y, then the age of y is greater than the age of x. This is what we have said here. That means that the difference between a function symbol and a predicate symbol is as follows. A function symbol like age x returns a value from the domain, whereas a predicate symbol like child xy returns true or false. This is the difference. A function is a mapping from D cross D to D, whereas a predicate is a mapping from D cross D to true or false. Now, there are more examples. Therefore, the age of a person is greater than the age of his grandchild. So, grandchild can be defined using child of child. So, you can say x is the child of y and y is the child of z. That is how you get grandchild. So, I leave this as an exercise. So, the next one is the sum of ages of two children are never more than the sum of ages of their parents. Now, in order to model this, we again need some new symbols. For example, we will require a new symbol sum xy, a new function symbol sum xy. This is a new function symbol sum xy, which will say add x and 2 and give the result of the sum. Now parents that we have here, the other is parents. We will require parent xy. So either we can define father and mother, or we can define parent as a predicate, or we can use the child function, child predicate, to define a parent predicate. Now it depends on how you want to use it. So I will leave this also as an exercise about how you are going to model these two. But as a summary, we had defined constant symbols. Constants get moved to functions with as soon as we introduce arguments, and propositions get extended to predicates. So now we had variables. So in first order logic, we had variables, we had constants and function symbols, propositions and predicate symbols, and these two new quantifiers which were added to Boolean logic to give us the predicate logic or first order logic. So this is the summary which we had done. So now let us discuss a few important issues that come up with this. Suppose I write down for all x p x y. Then we can see that this x is quantified by this for all x. So this x is a bound variable, whereas y is not bound by any quantifier. So in this expression, it is a free variable. Now we could write a more complex expression for all x p x y, and there exists z q x y z w. Let us analyze this carefully. If we analyze this carefully, we will notice that this x binds, this quantifier binds this variable. Whereas, since y is free, this y and this y are free variables. Similarly, this z is bound by this quantifier. This is a bound variable. This is a bound variable. X is bound, z is bound, and w is free. Now let us change this example a little. Let us change this example and let us extend it a little more. Let us write, and there exists z, there exists y, q, x, y, z, w. Now let us analyze what is the little difference between these two. X remains the same, it is bound by that same quantifier. Z remains the same, it is bound by this quantifier. W remains free. But this y and this y are different. This y with the scope rules is bound, whereas this y is unrelated to this quantifier, so this y is free. So we could replace this y by y1 and the expression would remain the same. Whereas in this expression, we will not be able to replace y by y1 or x by x1. So symbols, function symbols, variables can be quantified in first order logic as we have seen, and there are scoping rules. Symbols cannot be quantified. That means in first order logic, we cannot write there exists P for all x, P x. This is not in predicate logic. Whereas we can bound variables by quantifiers, we can bind variables by quantifiers, but we cannot bind predicates or any other function symbols by quantifiers. We cannot write there exists or for all with a predicate or a function symbol. Now we will see certain very important aspects called interpretations. Interpretation in Boolean sense, in propositional logic, an interpretation was an assignment of true or false to the Boolean variable. But now when we come to cases where we have variables, we have function symbols, we have constant symbols, we have propositional symbols, we have predicate symbols and quantifiers and function symbols, the meaning of an interpretation is more complex, and we shall see that in this lecture subsequently. Before we go to interpretations, to understand interpretations, we now try to understand the terminology of predicate logic. In predicate logic, we assume a domain D. This domain will be specified. The domain D will be specified for every interpretation. Then we have a set of constant symbols. In our methodology and our terminology, we will write constant symbols with uppercase letters. We will have a set of variables, and in our symbolic language, we have standardized the notation to write it out with lowercase letters. We have said function symbols are an extension of constant symbols with arguments. So we will have a set of function symbols which can have many arguments. Again, we can have predicate symbols with many arguments. And we will use these 6 connectors, the old 4 Boolean connectors, not, and, or, implies, and we will use the there exists and for all. Now we come to the 2 important things called terms. So how do we define a term? A term is defined as the following. Variables are terms. Constant symbols are terms. If T1, T2, Tk is a term and f x1, x2, xk is a function symbol, then f t1, t2, tk is also a term. Similarly, this is for function symbols. Similarly, if p x1, x2, xk is a predicate symbol, then we can augment this as P T1 T2 to Tk. What will happen here? This will become what is called a well-formed formula. So we say a proposition. So we come to what is called a well-formed formula or a WFF, and we say that propositions are WFFs and we say the same thing here. If T1 to Tk is a term and P is a predicate symbol, then this is also a well-formed formula. The other thing that we will add now is that if P is a well-formed formula, then not P is also a well-formed formula. If P and Q are well-formed formula, then P and Q, P or Q, and P implies Q are also well-formed formula, and they can be predicates. It is just P. A well-formed formula can be a predicate like this. Similarly, we have already defined free and bound variables. So what we say is that if Px is a well-formed formula where x is free in P, then for all x, Px is also a well-formed formula. There exists x, Px is also a well-formed formula. Now this P can have more arguments. But what we are saying is x is free in this P. So this is how I have informally, there is a detailed formal syntax and semantics. I will ask you to go through that detailed formal syntax and semantics. So there is a detailed formal syntax and semantics of predicate logic. I will request you to go through that. Once we have defined the syntax of Boolean logic or predicate logic, we now define how do we talk about a formula being true. In order to talk about a formula being true or a formula being false, we have to talk about what is called an interpretation. It is this interpretation which will enable us to understand whether a formula is true or false. So next we go and study whatever is an interpretation. Now let us go back to our original. In order to study this, let us go back to our original query on Mary and lamp. We had written for all x, we had defined the predicate goes, and we had defined these three, F1, F2, and G. Now, instead of goes, should it necessarily mean goes? What does goes mean? We could have written this. Instead of Mary, we could have written M. We could have written any symbol. Instead of lamb, we could have written any other symbol. It is the structure which is important. So, we could replace the predicate. That is why it is called a predicate symbol. It is just a symbol. There is no meaning to goes in just that expression. The meaning when we assign to goes, then we will have to define this predicate. And in order to define this predicate, we have to really start defining the domain and a predicate. So what is a function and a predicate? There is a domain D and a function from D cross D to D, let us say in the specific case. a function of two arguments. Let us look at this function f(xy) of two arguments. It is d cross d to d. For many arguments, a function will be d to the power n to d. Similarly, a predicate, here any predicate p which has got two arguments, let us say xy, is actually d cross d to either true or false. It will take two arguments from the domain D and give true or false. In general, a predicate P will be d to the power n to true or false. So when we define, so here is just a symbol, but when we define an interpretation, then we have to define what is the mapping. And once we define the mapping, then we get values for the function and we get truth for the predicates. And once we get values and truth for the functions and predicates, then we can assign truth value to the formula. And once we are able to assign truth value to the formula, we should be able to then decide whether the formula is true or false. So let us now go a little more deeper into interpretations and mappings. So what is an interpretation? An interpretation, as I just said, we have to assign, we were given a domain D, so assign the domain. For every constant symbol or function symbol, assign constants or functions from the domain. For every predicate, assign a specific relation, as we had seen here. If we saw this is actually a relation. Assign a specific relation from the domain. Once we do that, then the formulae that we have asked to be proved, like F1 and F2 implies G, that formula will have a specific value. Let us see one case of one interpretation that I have given here. In this interpretation, we have defined D to be 1, 2, 3, 4, 5, 6. This is one interpretation. So we have defined D to be a set having called Akash, baby, home, play, Ratan, swim. Then we have to define the following. We have to define what is the value of M. So let us say we define M to be home. Then we have to define what is L. Let us say we define L to be Akash. And we have to define S. Let us say we again define S to be Akash. Here it does not tell us that we have to take. So an interpretation can actually take some values. So the constant symbols will take some values. What do we have? We now have gxy. So we now have to define gxy, and for all pairs in D, we have to say whether gxy is true or false. That is how we define a specific gxy. So in this case, in this interpretation, if we define a specific gxy for all pairs, which will be 6C2 pairs, where we have to choose 2 at a time from them, and we have to choose, we can choose, even we have to choose Akash as one. So we have to choose all pairs of whatever we have, and based on that we have to give truth. Now once we have given truth, then we will check whether this formula F1 holds, whether F2 holds, whether G holds, and whether F1 and F2 implies G holds. So this is one interpretation that we have. We could define another interpretation. Please note that for this same domain, we can define many constant mappings and many predicate mappings. Each will give a different interpretation. We could also change the domain. For example, here we have said, let us say we define the domain as the set of integers, which includes positive and negative integers. And we could define gxy to say x divides y. Let us say we define these two. Then for every pair of x and y from this infinite set, we will get a truth value of whether x divides y or not. And we also have to do what is division by 0, and we may have to define division by 0 as no if it is to be divided by 0. X divides y means whether x actually is a divisor of y. It means that the remainder of that division is 0. Based on this, we will again check whether this formula F1 and F2 implies G is true or false for that interpretation. Given the set of integers, we could define many different functions. And then we also have to define the constant symbols L, M, and S. Maybe we could define all three to be 1. We could define L to be 1, M to be 2, and S to be 3, and so on and so forth. The interesting thing that we will see is that whatever interpretation we define, and you can imagine how many interpretations there are, the number of domains that there can be is probably much larger than you can imagine, because the power set of domains, which means it will be at least as much as the size of reals or the power set of the size of reals. Whatever you define, it is the power set of that size. That is the number of domains that you get. Given a domain which is infinite, you can see how many function symbol mappings, how many predicate mappings you can get. So it is an interesting question for you to determine how many interpretations can there be for finite domains and for infinite domains. Now, a formula is said to be valid if it is true for all interpretations. A formula is said to be valid, or a tautology, if it is true for all interpretations. In the case of a Boolean function, only true or false, because there are no arguments, there is only a proposition. So only true or false need to be assigned to a Boolean variable. But here there is so many assignments, and we have seen how large they are. And in order to prove that that formula is valid, for example, in this case F1 and F2 implies G, we know that this formula is valid. Whatever interpretation we put to this formula will always be true. This formula in this many case, irrespective of whether you define this domain or this domain or any other domain. And this formula is valid. So we really need to be able to prove that this formula is valid. A formula is said to be satisfiable if it is true under some interpretation. And a formula is said to be unsatisfiable if there is no interpretation for which the formula is true. A formula is said to be non-valid if there is some interpretation for which it is false. So interpretations hold the key to really finding out validity and satisfiability of Boolean formulas, especially in predicate logic. And we have seen how complex they can be in terms of predicate logic. Finally, what is the power of predicate logic? It has been shown that the power of predicate logic is the same as the power of computation. Predicate logic can model any computable function. So predicate logic can model any computable function. That is the enormous power that predicate logic has. But we also know that computable functions and computability has got another very important aspect, which is called the undecidability. And there are several problems which we know are to be undecidable, and I hope that any course in language and any course in formal automata and any course in computability theory will talk to you about some famous problems, of which one of them is the halting problem of a Turing machine. So which means that predicate logic is as powerful as a Turing machine. So since it is so powerful, it also comes with its limitations of undecidability. And there are many very logically interesting problems which are shown to be undecidable. One of them is the famous Russell's paradox. The Russell's paradox talks about three notions. It says that there is a barber in town. Those and only those who do not shave themselves are shaved by the barber. So there is one barber, and those who do not shave themselves, and only those who do not shave themselves are shaved by the barber. The question that is asked is, who shaves the barber? Now, there are two options. Either in this case, either the barber shaves himself, if the barber shaves himself, then this sentence is violated, because the barber shaves only those who do not shave themselves. So this is not possible. The other possibility is someone else shaves the barber. But this is also not possible, because we have said that there is only a single barber. So this is also not possible. So we see that this problem, which is a paradox, has actually no answer in predicate logic. Predicate logic cannot solve this problem. So it is an unsolvable problem. But even though predicate logic is unsolvable in the sense that if I give you a predicate logic formula, you do not have a general algorithm which will readily say whether it has an answer yes or no, because the answer could be a paradox like this. But if the answer is yes, Then there is a method. There are many methods, of which one of the most famous methods is the method of resolution refutation by Robinson. And that is a very unique and interesting method which does not need to traverse through all the infinite interpretations, but will work through a very, very interesting algorithm for which Robinson's work received the Turing Award. So that is why it is called semi-decidable. So it is, whereas in general first order logic is undecidable, but it is also semi-decidable. Second thing, the last thing that we will discuss is, look at this query. This query quantifies predicates, which is not allowed in first order logic. It says for all p, p0 is true, and if for all x px is true, then if for all x px being true implies p of sx is true, then for all y py is true. This quantifies predicate. This is not in first order logic. So this is higher order logic. But this is a very interesting query, and I will leave it to you to find out what this query tries to say. This query actually represents one of the most famous formulae, or one of the most famous theorems in mathematics, a theorem that all of us study, that theorem that all of us use. And this is a logical representation of the theorem, but that theorem is not applicable in first order logic, but it is a very famous theorem, and I will leave it to you to find out which theorem this is. With this, we come to the conclusion of the foundations and fundamentals of predicate logic. We have discussed how propositional logic moves on to predicate logic. We have seen how variables and quantifiers are there. We have seen how formulae are represented. We have seen the difference between function symbols and predicate symbols. We have talked about the structure, and then we have also talked about the interpretations. And finally, we talked about the power of predicate logic. Next, we will have to discuss how we solve problems and find out whether they are valid